Now we will discuss about how to represent graphs in computer. Representation of graphs in computer we are going to discuss. If someone tells you to draw any graph manually, you can very easily draw any graph of different number of edges. Let's say 1, 2, 3, 4, 5 vertices are there, let's say, and they are connected. And this is one kind of graph, you can say. This is a graph. Manually you can draw very easily. But in order to represent this graph in computer, you need to represent through some matrix. On that matrix, very popular two methods are there, and first one is known as adjacency matrix. Adjacency matrix, very popular, and this method is very much popular if your graph is dense in nature. If the graph is dense in nature, then normally we prefer adjacency matrix, or we represent our graph by using adjacency matrix. But if the graph is sparse in nature, then we use adjacency list. So that is a linked list kind of things that we basically maintain. But this method is very much popular if your graph is sparse in nature. And both has its own time complexity. So adjacency matrix, I will explain you how basically it goes to the order of n square. So its time complexity will come n number of vertices and number of edges, you can say order of n square. In terms of space complexity, this is order of n square if you are representing your graph through adjacency matrix. But if you are representing through adjacency list, its time complexity is roughly coming around n plus twice of e. Why 2e? That I will tell you. So one list you are maintaining from this end to this end, another edge you are maintaining from 2 to 1 to 2 path you are maintaining. So total space will be required, number of vertices plus twice of e. So it depends on the kind of graph. You may be preferring either adjacency matrix or you may be preferring adjacency list. But what is basically adjacency matrix? It's nothing. It's basically a two-dimensional matrix. Let's say n cross n. So this is our 5 vertex. So I will number like this: 1, 2, 3, 4, 5. So these 5 vertices are there, and similarly you have 1, 2, 3, 4, 5. If there is any path available between them, you will represent simply by using 1. This is not a directed graph, this is undirected graph, so path will be maintained between, let's say, 1 to 2, then 2 to 1 also. So 1 to 2 it's a 1, and 2 to 1 also it will be 1. And if there is any self loop kind of things, then you will represent that cost or that particular path. But in this graph there is no loop, so all the diagonal element 1 to 1, 2 to 2, 3 to 3, 4 to 4, and 5 to 5 will be 0. So they will be represented as a 0. So it's a very simple representation. You can simply write 1 if there is path available, else you can write simply 0. So in this way you can maintain for this particular graph 1, 1, and this could be 0, and this is basically 0, 1, 0, and path is available between 3 to 4 and 3 to 5 also. So 1, 1 path will be there. And for 4, you can write down here 4 to 1 path is available, 4 to 2 is available, 4 to 3 is also available, 4 to 4 self loop is 0, so you're writing 0, and 4 to 5 path is available, so you're writing 1. So no path, 0, 0. If there is path, 1. If there is path, there is path. So this is nothing, basically a 5 cross 5 adjacency matrix. Adjacency matrix of your given graph, example graph that we have taken. So in this way you can represent your particular graph in computer memory. So it's basically nothing, n cross n. If there is an edge, you represent it by 1. If there is no edge, you represent it by aij equal to 0. So similarly for adjacency list, you could maintain like adjacency list in a form of linked list. So number of vertex, so depends on the number of vertex, you basically takes that much number of list. So first list will be representing the node 1 or vertex 1 having link with 2 as well as it is linked with 4. So this kind of a structure you maintain. Similarly for second node, you could maintain a structure like 2 is having connection with 1 also, it is having connection with 3 also, it is having connection with 4 also. So this adjacency list you are maintaining for 2. Similarly for 3, similarly for 4, and similarly for 5. For 3 you can maintain like this. For 3 you can maintain like this. 3 is having path width, let's say 2, and then it is having connection with 4 also, and it is having connection with 5 also. Similarly for 4 you could have path to 1, you could have path to 2 also, path to 3 also, and path to 5 also. Similarly for 5 you could have a path to 4 and path to 3. 5 you have path to 3, 5 to 4 also. So this is nothing, it is basically a representation. 5 different list or linked list you are maintaining, and that is nothing, that these are basically adjacency list representation of your given graph. So this could be something like related to, you can say, very simple method. So adjacency matrix or adjacency list, based on your choice you could use, but roughly I have stated you, for sparse graph you basically prefer your adjacency list, and for roughly adjacency list or matrix is normally we use for dense graph. If the graph is very much dense, every edge or every vertex is connected to every other vertex, then that graph is known as dense graph. So adjacency matrix and adjacency list are the two popular approaches for representation of a graph. In the next video I will tell you how to traverse graph using BFS and DFS. Thank you.